An interstate toll booth experiences, during a particular time period, an average of 2.5 cars per hour. If X is the number of cars using the booth during a 1 hour period, find the probability distribution. Okay, so there's not a whole lot of information given here. And anytime you're just given an average, you're just given a value for the mean, either directly or indirectly, then that tells us that we're dealing with a Poisson process, a Poisson random variable. And so the mean is given, that's going to be 2.5. So again, the Poisson distribution is used when you have rare events. Only 2.5 cars per hour, but there are, basically it's a rare event, even though there are a lot of quote-unquote trials. In other words, there's a lot of hours, a lot of minutes. So we can use the probability of the Poisson formula So the lambda for all of these is going to be 2.5. And e to the negative lambda. Okay, so this number, whatever this comes out to be, this is going to be the same, whether we're figuring out x equals 0, x equals 1, x equals 2. It doesn't matter, right? So, in other words, we can figure this out right away. E to the negative lambda. And E is about, that's 2.5. E is about 2.72. You can do it that way, or if your calculator has an E key, which it probably does, any scientific calculator would have an E key. So 2.72 to the negative 2.5 power gives us 0.0, I'm going to go with 0.0821. In intermediate steps like this, you want to use as many decimal places as possible because it's not like you're rounding off a final answer. This number is going to go into other formulas, and that number can go into other formulas, and so any rounding error is going to get compounded. So you don't want to be stingy with decimal places, especially since you already have a calculator already. It's not like you have to calculate these by hand. Okay, so the probability that of 0 cars. Well, okay, so it's going to be 2.5, that's our mean, to the 0 power, because x equals 0. E to the negative lambda, e to the negative 2.5, we already found that. That's going to be the same for each one of these. X factorial, 0 factorial. So really, you have this is 1, this is 1, and so it's just going to be 0.0821. Now that's the final answer, we'll round off to the usual 3 places. And we're just going to continue like this. We'll do a few more of these. X equals 1, 2.5 to the 1. Over 1 factorial, so we're just going to take our previous answer and multiply that by 2.5, since we have 2.5 to the 1 power this time. 205. All right, let's keep going. Probability of 2 cars, exactly 2 cars. 2.5 squared. The same 0.0821. Remember, this is just e to the negative lambda. That's not going to change. All this is a constant to the mean, which within this problem, the mean itself is a constant. So 2 factorial, so we're going to multiply 2.5 squared times 0.0821 divided by 2 factorial, which is just 2 itself, and we get 0.257. we might go up to 6 here. X equals 3. If the average is 2.5, then we should hit our mode somewhere between 2 and 3. Let's see, 2.5, now it's 2.5 to the third, to the 1, to the 2, to the 3. Over 3 factorial, and 3 factorial is 3 times 2 times 1, and that's equal to 6. So 2.5 raised to the third times 0.0821, whole thing divided by 6, and we'll get 0.214. So you see we've hit the mode here, 2.257. We're a little bit lower now because the mean is 2.5. So we kind of passed over that hump, and now we're going toward the right tail of the distribution. So x equals 4, 2.5 to the fourth. 4 factorial is 6 times 5, 4 times 3 times 2 times 1. And we multiply this out together, we'll get 0.134. X equals 5. And we'll do 2 more of these. X equals 5. So 2.5 to the fifth. 5 factorial, in this case 24 times 5. You multiply that all out, it comes down to 120. And this becomes 0.067. And we'll finish up with 6. I think that'll give us a decent idea. So 2.5 to the 6. 1. 6 factorial is this number, this 120. Now we're going to multiply that by 6, and we get 720. And that will give us 0.028. So I believe by this point, our cumulative probability, if we add all these up, you know they have to add to 1, and eventually they will. Of course, even though we have an infinite number of possible values for x, I believe we're up to about 0.998 or something like 998,999. So as we go forward with 7, 8, 9, 10, these numbers are going to become very tiny after a while. We can make the distribution. We can draw out the distribution here by making a table of values. Don't worry, we're not going to find the mean and standard deviation of this. Although if we did, it would be, if we found the mean of this distribution by the x times p of x, it would come out to 2.5. Maybe a little less because we're not including all the values of x here. And of course, you could set this up in a histogram or a dot plot, let's say. I'm just going to kind of eyeball it. So we have 0.082, let this be 1. So 0.082, that's 0.08, that's maybe here. 1 is 0.20, 2 is about 0.25, 3 is about 0.214 again, 4 about 0.13, and you can see that it starts to bring it to that point. So we see it's a right skewed distribution. That's to be expected since mu is such a small number, the mean is such a small number.